And you're recording now.
Good afternoon. Matt Miller. We're here at the Cornell High Energy Synchrotron source talking about diffraction and Darren Pagan's diffraction class today. We're going to talk about lattice strains and crystal stresses. So the course note packet for this particular this particular lecture is just called Crystal Mechanics. All right, so today we'll talk about the idea of measuring lattice strains using diffraction, and how do you do that in a systematic way and turn that into information that you can use in a kind of a mechanics format. So here's the nature of the problem we're after. We have a polycrystalline aggregate, so we have lots of crystals in here. And it's being loaded. We'll give it a simple macroscopically uniaxial load. And we want to determine the stresses inside every one of these crystals. So what I'm saying is that using the methods that you guys have been developing over the last few weeks, we can actually do that. We can actually get the stress strain curve for every crystal inside of that aggregate, which is kind of cool. So if we go to, if we look at a conventional experiment, so let's go take a quick look at a uniaxial experiment. So we see the tensile sample with an extensometer mounted on it, and that little extensometer, basically it measures the difference between 2 points on the sample, and then the electronics calculates a strain. The stress in this sample is just the load over the area. So a couple of things. We also have a set of basis vectors there that we'll talk about. But we start with this as kind of the starting point of our discussion. Okay. So if we envision this this aggregate as being inside of the sample, inside the gauge section of that sample. Again, what we're really looking to understand would be the state of stress and the value of stress inside every one of those crystals. So we start off making sure that we define our stress tensor macroscopically. And we just put it in matrix form, and we have our set of basis vectors in the and for this uniaxial experiment, just by the nature of the way that it is set up, that the only non-zero value of stress in the stress tensor is just the load over the area in the E3 direction. So our strains so for elastic deformation, the corresponding strain tensor So we have slipped in this definition of our normal strain, the first definition of strain that you've probably ever heard of, that the strain is just the change in the length of the gauge length, the change in the length of the gauge section over the initial section. So this is the engineering strain tensor, and if it's an isotropic material, then if this is epsilon 3,3, then the other, we know what the other two values, non-zero values of the stress of the strain are. So again, just as by way of completeness, if I load a sample, a lot of the things that we do here, and a lot of times what people are interested in is what happens when you load polycrystalline samples. That's really one of the real strengths of some of the high energy X-ray methods, is watching this in situ. So we look at a macroscopic stress strain curve. Again, this is sigma 3,3, epsilon 3,3. Now we're gonna go beyond elastic deformation. We'll load up, and we have these regions. Here's what's called elastic. This region is called elastoplastic. We can determine the plastic strain. We call this epsilon 3,3p, and the elastic strain, epsilon 3,3e. Somewhere in here we've defined probably a yield strength, but this is a typical stress strain curve for a polycrystalline metal. And so one of the things that we're often interested in is, as we're going along this stress strain curve, how are the stresses and strains changing inside of every crystal? So that's what we're going to kind of talk about. Looks like there might be a couple questions. Okay. All right. So let's take a look at, from what you guys have done in diffraction, how would we define a strain? What I want to do is I want to define a diffraction related quantity, this delta L over L naught. And so if I think of a diffraction experiment, I have a crystal here's our vector that I think this is consistent with the nomenclature, K in and K out, and the scattering vector is Q. And so we have a point on the detector, and so strain is one thing to kind of understand is strain is a before and after. Yeah, let's make sure we got lattice strain in here. Lattice strain is a before and after measurement, and so with in an in situ experiment, you're there for the before. The before is like without any load, but you haven't loaded the sample. If it's an experiment on a piece that you know has strain inside of it, you weren't there for the before part. And sometimes that becomes the challenge, is kind of trying to understand what that configuration was before. But there's always, strain is always about a delta. It's always about a shift. And so remind ourselves that every point on the detector can be parameterized with 2 theta, eta, and omega. Remember, in the rotating crystal experiment, we rotate about a vertical axis, omega. Our azimuthal direction is eta, and 2 theta is the Bragg angle. So you can parameterize, and Darren has had he's had the detector often just with an XY coordinate system, and so you can do that, and you convert the XY to these kind of polar coordinates. But I think the most important point about this measurement is I have a diffraction spot in the unstrained configuration, and then what I really want to follow, I want to follow that spot as I strain it, and so it's really this delta. So it's a kind of a before and after. So if I parameterize this, every point here, I can, and remember at when the fraction is taking place, Q is equal to G, the reciprocal lattice vector. So I can get from the point about just in general thinking about how you extract this from your data. I can get a point associated with every scattering vector or reciprocal lattice vector that I'm measuring. So everything kind of comes out in terms of 2 theta, eta, and omega. And I'm trying to remember whether you guys had derived the expression relating G to 2 theta and eta. And that's something that's done in the notes. But you can kind of write this. Basically, you can derive the following, that so G, the lab frame for a particular HKL, is equal to lambda. Again, you can derive this. And so the main point here is, though, that every G is related to those 3 things that we measure in the course of an experiment. So now if I take if I look at the relationship between D, this is the lattice spacing. I can relate D is equal to 2 pi, and this is something that's been derived. 2 pi over the magnitude of the scattering vector, the reciprocal lattice vector. And so I can look at the idea of an InSitµ experiment is to measure G initial, I'll call it O, then measure this G, and from these we can determine a change in delta G. We can calculate the delta G, And then we can determine a delta D. That's what we're going to do in the next board. So again, the steps. You have 2 theta, eta, and omega for every spot. You watch the spot shift. So you have now you have an initial G, you have a final G. So literally you'll have a column of G vectors, and you do the delta between before and after. Now this is all in terms of the kinematics here. Some of you mechanicians might be kind of worried that we're really doing this in a small strain configuration. Well, for metals, small strain is fine. Small, because what we're thinking of is small strain, small elastic strains. So most of what we do, we're able to employ the infinitesimal strain tensor without any significant error. So let's define another thing. We'll also define the N, the D, and that's defined as G over the magnitude of G. I'm going to probably drop the HKLs at some point. So let's go back to our engineering strain. Delta L over L naught. Well, we use the N to define epsilon N as delta D over D naught. We'll put this up here. So it's exactly like the normal strain that we defined in the tension test. So let's kind of carry that through. So delta D over D naught equals D minus D naught over D naught. And again, these all have HKL beside them. Which also equals D over D naught minus 1. And then we use our expression that relates G to D, and we get epsilon NN G naught over G magnitudes minus 1. And this is our expression for strain. So go back and do it again. You have a diffraction spot. You measure the G vector knowing 2 theta, eta, and omega. You watch that spot shift. You calculate the new G vector. And this expression then enables you to calculate the normal strain associated with this particular set of lattice planes in a particular direction. This is along the scattering vector. Okay, so this is one component of a strain tensor. And what we want is, we always, even though sometimes we only talk about strain as being a number, strain's a tensor. And in this experiment, that's what we want to determine. We want to determine the lattice strain tensor because in the end, we want the stress tensor. So the idea that we can, I want you to appreciate that you can measure the lattice strain, and we'll talk in just a minute about how we know that lattice strain is actually elastic, because it's important that it is, because we're going to use it to calculate stress using Hooke's law. So we've calculated the lattice strain from our diffraction data. So we have a data set. We've collected these images, and we go in and do the magics to find the spots and determine what those G vectors are, and now we can determine the strain. So let's talk about what we do with these normal strains. And to do that, I want to go back to something that I think many of you probably have in your background. Certainly the mechanical engineers, material scientists, I bet will have some of this in your background. We're going to go back and talk about stress analysis. Using strain gauges. I hope you can appreciate that this crystal lattice is like a tiny little strain gauge. So how did we do this back in the day? What did we, back in your mechanics and materials class, if you were fortunate enough to take that and had a lab associated with it, the idea was to determine the state of stress. So basically always I want sigma on a surface of a component. Well, the surface part tells us that this is plane stress. So what I wanted usually would look like this, sigma again, kind of a coordinate system. This is what plane stress looks like. So there are only 3 non-zero components of stress for plane stress. And for an anisotropic material forming elastically, we would hope, epsilon sometimes I write symmetric, sometimes I actually put the component in there. You know, don't get too worked up about that. Well, we know this, and you know, plane stress does not imply plane strain, so we always have this non-zero component of strain that for isotropic elastic deformation would be related to Poisson's ratio. So this is what we want. And so first of all, can we measure stress? Is stress a quantity that we can experimentally, with no conversion other than converting? Can I directly convert? Well, it's hard to say. Let me just say that you can't measure stress. Okay, can't measure stress. So what we typically do, we typically measure strain. In our business, we measure strain and compute stress. In everybody's business, people doing tension tests with a load cell. You're measuring strain, converting that to stress. So the idea is I want to measure this strain tensor, and I want to compute the stress tensor. That's the idea. So I need to go in and measure these components of strain, epsilon 1,1, epsilon 2,2, and epsilon 1,2. So how do I do that? Well, what I really am not great at, so we just talked about how to measure a couple of these normal strains, pretty good at that. We kind of suck at this, quite honestly. So, plus there's a systematic way of measuring normal strains and turning it into this. That's what we're doing. That's what we're going to talk about. So that's what the premise of stress analysis is. So the idea is to measure so here's the recipe, stress analysis. First of all, how many I have 3 strain components that I need. I can calculate epsilon 3.3 using elasticity. So I need 3 normal strains, but stress analysis basically, so I need to measure at least convert. What does that mean? Measure at least 3 normal strains, convert the normal strains to the strain tensor, and again, these are all, we are right now assuming that these are all elastic strains. Convert the normal strains to the strain tensor, and then compute the stress tensor, which we know to have 3 non-zero stress components. So that's the recipe, and so here's the operationally how you do it. The reason we're kind of slugging it out with this is that when you get lost, and you will, when you get lost in the middle of data reduction, when you're reducing your diffraction data for strains, you're going to need a trail of breadcrumbs back to where all this stuff came from. And so this is hopefully providing you with part of that trail of breadcrumbs. If you can get back to the place where you're thinking of strain gauges, you'll probably be able to find yourself out of the woods and away from the wicked witch. So what we do is we take 3 gauges, A, B, C. We have 3 angles, and unfortunately, everything's theta. You know, what can I say? This is not the Bragg angle. This is the gauge angle, but this is often what we write. Theta B, theta C. 3 strain gauges, 3 angles. And so the output from those strain gauges, you know, you run this through the Wheatstone bridge and you do all the good stuff. You measure what you would call, back in the, like when you did stress analysis, you measure epsilon A, epsilon B, and epsilon C. Well, in reality, what you've got going here is you've got a coordinate system that's relevant, your XY is relevant to your sample somehow. And the way we're going to think about this is for each one of these gauges, for each gauge, we're going to transform our strain tensor. We want, remember, here's what we want. We want epsilon in the XYZ coordinate system. It's probably not the right way to write that, but I want the components of strain in the XYZ coordinate system. What I'm measuring now, I'm measuring 3 normal components in 3 different coordinate systems. So for each gauge, I transform, so I'm transforming my strain tensor, the thing I want, to a new coordinate system. When you do stress analysis, you end up with these set of equations that oftentimes you have no, you can find your way through it if you've done it a few times, but just a set of epsilons and sigmas and stuff that on first glance you can't even really make any sense of it. If you feel comfortable with the concept of a tensor transformation, you'll never be confused by strain gauge analysis again. So this is what we're going to do. We're going to do this two ways. So remember, what we want is this. This is what we want, and these are what we measured. So we're going to do this two ways. These are going to be what's called the Rosette equations. Let's go take a quick look at a picture in the course notes. Reminds you of something from back in the day. I've kind of jumped around a little bit, as you can see. So the figure on the left, that's called a linear strain gauge. That's your crystal lattice. Figure on the right is called a strain gauge rosette. It's a set of 3 strain gauges. That's just terminology. So in the stress analysis business, okay? So these are referred to, even in our business, in this diffraction business, we will call these often the Rosette equations. And all that means is the set of equations that take the lattice strains that we measure for the crystal and determine the crystal strain tensor. So here's, I don't want to get ahead of ourselves, but you'll hear the term Rosette equations, when we're talking about diffraction, all right? We're going to do this two ways. First of all, we'll transform from XYZ to X prime, Y prime, Z prime, and then we'll talk about the second way. So let's do this. Let's define our coordinate systems. So here's the old. Remember when Darren derived the transformation equations? We're going to call this theta I, and I goes from A, B, and C. Well, and our basis in this coordinate system, here's our original basis, E1, E2, E3 is coming out of the board. Here's our new basis, E1, E2 prime, and E3 prime equals E3. So this is a simple coordinate transformation in that we're just rotating about the z-axis. So we can go in and remember how we do this. We write this, we write E1 prime in terms of and this is theta I, not theta 1. This is an I. I would like to say that I'm going to always put the little things on it, but I may not. So you guys just remember that. And remember, these are basis vectors, so they'll have little hats because they're all unit vectors. and then E2 prime in terms of now, transformation equations, remember how this goes. We write epsilon, we write this in official notation, ij is equal to epsilon kj, I'm sorry, epsilon kl, a ik, a jl, where A is just the dot product between new, old. So the I is with the new, the J is with the old. Remember also, be very careful, and Darren said this before, but make sure that you know how people are defining that transformation matrix, because that's stripped up more than one mechanician over the years, and that some people define it the other way around, and then your transformation equations are the transpose of what you did. So let's talk about what A looks like for ours. So A and Darren did one like this before as well for the rotation. So now we're going to do in matrix form, epsilon prime is equal to A epsilon A transpose. So we're going to do that, and we're going to end up with, and in the notes, you kind of actually go through and slug it out and do that. That's kind of exciting. Let's write this down. We end up with the following. And you have something in all these. I mean, so, but this is the only one we're interested in, right? Because all we're really interested in this new coordinate system is epsilon x prime, x prime. That was the one that was along our x prime axis. So, you know, again, the main reason to do it this way is to show you that this is a tensor transformation. That's what this is. That's what strain gauge reduction is. So then I do the same thing. Remember, we do it for all three gauges. Theta A, theta B, theta C. And we end up with the following set of equations. epsilon A, function of beta A, cosine squared, beta A, epsilon 1, 1, plus sine squared, beta A, epsilon 2, 2, plus 2 sine beta A, cosine beta A, epsilon 1, 2.
That's epsilon A prime, right?
Correct. No. This is just epsilon A. I mean, this is in our first coordinate system. Very good question from you. So we imagined that this A direction was x prime, and then we did the whole thing again, and we imagined this. So the primes kind of go away. The primes were sort of there, the intermediate stuff. Really good question. We write the same thing for all the other two. Yes, this is, so in this coordinate system, I'm just getting back to that. This is epsilon x prime. I may have said it incorrectly. So always really there's two indices on a strain. So it's, okay. Finally, epsilon c of theta b, theta c. So I'm pretty sure there'll be some mistakes up here, so I'm relying on my in-class participants to hold me accountable. Cosine theta. Okay, so I have three equations, and I think I'm off the board, right? A little bit, sorry. Three equations, three unknowns. So I solve, because remember, this is what I know. This is what I've measured. These are what I want. Right, so I have a set of linear equations. So I solve 1, 2, 3, 4, epsilon 1, 1, epsilon 1, 2, epsilon 2, 2. And then from here I can compute epsilon 3, 3 because it's plane stress. So I have my strain tensor. That's what I wanted. Now we're going to do this again, and we're going to do it in a more general way, because what I'm hoping to be able to convince you is that we're doing nothing more for our in situ lattice strain experiment than we're doing nothing more than this simple stress analysis problem. But if I think about it, let's draw a picture. Let's draw a picture real quick. I keep wanting to jump ahead, I'm just so anxious to get us to lattice strains that I guess keep jumping ahead. So what can I say? Here's our crystal, and it's nicely just a nice little cube. And we want, remember, I want sigma, so I do that by get the strain tensor. So what I'm going to do, I'm going to use the expression that we derived the very first. I'm going to look at lots of different g vectors. G1, G2, G3. And the way I'm going to do this is, first of all, I'm going to look at all the spots at 1 omega, then I'm going to rotate it and look at all the spots at another omega. So I'm going to gather lots of delta G's. Okay, I'm going to watch it. It's going to be a before and after, right? But they're not going to be in the plane, right? So our strain gauge, we want to make our strain gauge derivation a little bit more general. So with the strain gauges, the transformation was always around that E3. Now the transformation is going to be all over the place. So let's talk about that. And so I actually am not going to derive this. I'm going to let you guys go take a look at this in the course notes. And I don't know that Darren has used this property of the dot product in the tensor. But you can very elegantly show, that epsilon n is just equal to n dot the strain tensor dot n. So again, one definition of a tensor is it operates on a vector space producing another vector. Then you're just doing a dot product with that. So that it's not, you can almost convince yourself just looking at it that this is true. And so now remember our n's here. For us, n is just g over magnitude g. So we have our n's. So in reality, we have in our data set, we have the delta G, we have the N, and we can determine we can write this set of equations. So let's do that though. Let's write this system of equations. Looks like a bomb went off, isn't it? Let's write one of these out. So the idea is I'm going to have lots of these. These are my measurements. And this is what I want, remember? Seems like that's always the case. The thing that you want is buried inside of an equation somewhere. That's just the way life sort of works. So let's write one of these out. So this is from one lattice strain measurement. I'm just keep writing that because this is your, we'll track this all the way back, right? This is our delta D. This is our delta G. This we get from the expression that we can, because we can always compute the G vectors. And so we can always look at that quantity. We can measure that. We can extract that from our experimental data. So now then we can write this in a matrix form. So I'll let you write this down first. But we're going to write this in a matrix form because remember, in typical lattice strain measurement experiment, we'll have 20 to 50 of these, maybe more, depending upon crystal class and whatever, and just how far we rotate our sample. So we're going to have lots of these, and now we need at least 6. So I need at least 6 measurements. So for a crystal under a general state of stress, I need more than, I need at least 6. This is something to kind of remember, because we're talking, right now we're talking about lattice strain measurements for individual crystals, but this generalizes almost perfectly to looking at a powder sample, where now we're interrogating lots and lots of crystals. And one of the things that we often, one of the things that happens a lot is people will come in and only want to make 2 or 3 lattice strain measurements. Say it's a complicated part and it's a residual stress experiment. If this is a point, which we can do, if this is a point deep within a part and there's no free surface, you have no idea whether or not that's how many components, how many non-zero components of stress that point is going to contain. So you've got to make 6 measurements. So let's write this in matrix form. Sometimes you can get away with fewer than 6. If you know something about perhaps the way the material was processed, or if you have some idea, if you modeled a process, or you've got some sort of knowledge beforehand, maybe you can make an assumption that will reduce that. And often, I will do that for sure. But just jumping in there and saying, well, I'm just going to measure it this way, and I'm going to use E and nu, and next thing you know, bridges are falling down, aircraft are crashing. All right, so let's use the following kind of terminology. Excellent, and I'm going to call this so let's start. Let's do this kind of in a more. So multiple lattice strain measurements. We'll call it epsilon n, and we're going to use a comma. This is not, we're not differentiating. We're just going to use this for this. And so we will write it's in matrix form as the following. That'll be fine. Epsilon n, and this is the ith measurement. Remember, I said I can go from 20 to 50. So epsilon n 1, n 1 comma 1 squared, n 2 comma 1 squared, n 3 comma 1 squared, n 2 comma 1, n 3 comma 1, and 1, comma 1, and 3, comma 1, and 1, comma 1, and 2, comma 1. And then over here, we have our strain written in a vector form. Um, 2 epsilon 2, 3, 2 epsilon 1, 3, 2 epsilon 1, 2. When we talk about elasticity in a little while, we're gonna do this again, and this is a typical ordering for when I take the strain tensor and turn it into a vector. You do the normals, then you go 2, 3, 1, 3, 1, 2, and you put a 2 in here. That takes care of the fact that there are 2 shear strains. So then I just keep going, right? So now I have n 2, and so you kind of just would have a system of equations, and if you just have 6, you solve this directly, or you can solve for the least squared. And you end up with a strain tensor. Okay? So that's strain. What about stress? Well, we'll just do a couple of things here. And again, we've done all of this. Let's make a couple of notes. Well, at the point of where we're just talking about strain, I'll make a couple of points. So we derive this expression, our expression for our transformations for a single crystal. So if our sample, again, I'm sort of thinking of an in situ loading experiment. If our sample is a single crystal, then we're done. Life's good. What about a polycrystal? Because that's usually what we're dealing with in engineering materials, structural metals. Well, 2 questions you have to sort of think about. Well, actually, the first question. So this. First question is, what's the ratio of the beam size to the crystal size? And another way to think about that question is, and this is actually the way that you always, end up finally answering this, even though you have some idea of what you're going to get, are my data rings or spots? That's sort of the first question, or the most important question is, so am I going to do this they're always on the Debye ring, but are they solid rings? Is this a powder experiment, what we refer to as a powder experiment, or is this what we call an individual crystal experiment? Let's say the answer is spots. So let's talk about the spots. So remember, our derivation was for a single crystal, but rarely will you have a sample that's a single crystal. So you're always going to have to deal with more than one crystal. So if I have spots, so now we have to think about which spots that should be the one that's really making you nervous, because the spots are on the detector, and it's coming from a crystal that you can't even see, and so this is a very likely, this is a place where you're instantly get stymied, and luckily, there have been people that have worked this out for us, and we've kind of built off of that. But I think a lot of this will be based on work that first came out of the group from RISO. And so you got to work this out, right? So you're going to figure out and I'm thinking that Darren Pagan next week will be talking about that. So that's the first thing you have to do. The good news is that there's enough information. What's really cool, and it still just kind of amazes me, there's enough information to not only get, so from this rotating crystal experiment, you will get rotating polycrystal. Now, Darren, I think it was last week, actually did talk about what happens if your crystal is not on the rotation axis, and you define this other vector, and now you kind of got to do this stuff. Well, that's what you sort of do. So from the rotating polycrystal, you will get the orientation of each crystal. And I don't know about the subscripts, superscripts, but you get it for each crystal. You get that, you're going to get the strain tensor, and you're going to get the position, which is pretty cool. So you're going to get the position of the centroid. And this is in the far field. This is at a meter or beyond. This is where you're doing these experiments. So all of this is going to come out of your data reduction, which is pretty cool. And it's basically geometry. And so that's all going to come out. And so then you go on with your deal. Actually, what you really want to know, what will come out of this, what will come out of your raw data, is you'll get your G vector for all of your points associated with that crystal. Then you're going to calculate your epsilon. So you get all the G vectors. Kind of neat. Sort of looks like magic a little bit, but it's not. What if this is rings? Now, I'm going to carry this piece of paper around with me because I'm in total BS mode right now. If it's rings, so now your detector looks like this. And then this is before. And this is before you load it, before load. And this is after. They look exactly the same. I mean, when you're just looking at it, but remember, these are subtle. This is subtle. This is a displacement. That delta is something that you have to actually determine down to a subpixel resolution. So the actual fitting of that spot, even if it's a spot or a ring, that's not trivial. And I don't know if that's being talked about next week or not, but there's going to be some fitting. In 2 weeks, we're going to talk about fitting the peaks. So I'm assuming that you got all that done, and that's this lecture, because they won't let me do the harder lectures. So this is before the load, this is after load. So this is subtle, right? That's the point. Now in reality, these rings have now moved. If I'm loading the sample, if my sample looks like this, so I'm loading in near in this direction towards the top. Which way will the rings? So the rings go from being perfectly circular, sort of, to not circular. So how will they change? So that the D spacings in this direction are getting longer. Poisson said the D spacings in this direction are getting more contracted. So how will the rings change? Well, the rings are kind of more about 2 theta, so the rings actually get shorter in this dimension and longer in that dimension if you're loading it that way. But what you really can't do, and trust me, when we got into this business, we tried it all. Because I think when we did our first set of experiments, New Year's Eve 2001, I hate to even think about it. How crudely we did this, and how I just expected this shift to be like an inch. I just thought this thing is going to go crazy. Well, I hadn't really thought that through, and then luckily I had there were calmer minds prevailed. Joel Bernier was the student working with me at that point. Joel, I'm sure you're watching. And so basically, this is subtle. This does not become what you would like to say that, okay, it becomes elliptical, and we can just look at the ellipse. Well, anyhow. But how do I get to, let's have a question. So how do I get to my delta G? What's that? How are you going to do that? And Darren will probably talk about this at some point. So what you do is you break this thing up. So you divide this up into sectors, and maybe you do 5-degree sectors, and then you integrate these sectors in omega and take an average. So because you want to kind of combine all of this data. So then you'll end up with a single value at the centroid of each one of these little sectors. And darn if that doesn't look just like spots, right? So now we're back to our usual thing. Now the issue with powder is, though, I have no idea about. I have some idea, but I cannot identify the individual crystal associated with each one of these with their a point. So if I'm just thinking of a point on one of these rings, I cannot identify the crystal. So really what's happened is that I have so many crystals There's so many crystals in the diffraction volume, there are still spots under here. But now there's so many spots that they just overlap. And so I can't do my cool little magic thing that I do with the spots and identify which strains go with which crystals, or which spots go with which crystals, because I don't know. And the other thing is, if I think about what's going on, that diffraction experiment right there, remember that if I and I'm going to draw a really kludgy looking Bragg's law here, but all I know is that this is G and it's equal to Q, this particular Q. So this thing, this value of G out here, which I can always determine because I have 2 theta, eta, and omega. That's all I need. All I know about the crystal that created this diffraction intensity is that this set of lattice planes were pointed like this. Okay, so X-ray goes through the sample, and it goes through and it's asking everybody. Remember, this is a monochromatic experiment. It's going through and asking everybody, are you oriented like this? And some are. So there's not just one crystal like this, right? Because just because I have this HKL oriented like this, I can have another crystal that's rotated about this scattering vector, that's rotated about. So this has one matrix, this has another rotation, they're completely different. Now they're related, and Darren may or may not talk about how they are related and how they look in orientation space. But what I can sort of tell you, one of the really good reasons for using a Rodriguez parameterization orientation space is that the crystals that in a powder sample, the crystals that make this intensity all lie along a straight line, and that straight line, I'm writing all over the place. So you guys, if you fell asleep or if you went off and checked your email, you're completely lost. But that's why you don't go check your email. So that spot lies along what's called a fiber. A fiber in orientation space. The cool thing about a Rodriguez parameterization is that fiber looks like a fiber. It's just a line, and so it's great. So anyhow, that strain now is associated with all these crystals that lie along this fiber. So the question of what you do with that is what we're going to talk about now. And that is, how am I going to take these strain, how do I compute the stress? And what stress is that? Let's go back to our simple single crystal. So here's what I want you to write down in the margin of your notes. Write down. I want you to write this down because you talk about a rabbit hole. You will get way down the rabbit hole looking at strains. You're going to be looking at files someday, and you are not going to know up from down. And if you can take yourself all the way back to the single crystal, and then take yourself all the way back to the strain gauge and the rosette, and then find your way forward. That's the way forward. And if you get lost, because you will, I promise you will. And the other point that Darren made several times, and I'll make again, is, and then being careful when it comes to rotations, transformations, all that stuff that we taught, that he very carefully derived for you. That's another place that you'll get screwed up. So, very first thing you want to do is you want to do problems that you know the answer to. That's the experimentalist's first bylaw. When you get your experimental ring, I don't know. Let's talk about stress. Let's go back to the single crystal. All right. Let me write Hooke's law. So remember we have I'm gonna put a little C right there. We have the strain tensor associated with that crystal. And we have it relative, there's going to be some coordinate system. So we're going to have, we also have this. So remember, there's a difference between this and this. Tensor matrix. These are the components relative to a coordinate system. So if I have these relative to a coordinate system, I can calculate the stress. So we want, remember, we always want this. Then we do whatever we want to. We can take this and transform it and do whatever we want to. If we have epsilon in a coordinate system, how do we get stress? Well, in Hooke, they said, well, here's what you do. You take, so the simplest expression for is basically say, and remember this is using additional notation. This is, of course, this is a second order tensor, fourth order tensor. And so inside this, you have 81 constants, 3 to the 4th. And so Hooke, it's like it wasn't like a real deep thought. Well, it was pretty deep. But he just said, you know what, I'm going to say that every component of stress can be a function of a linear function of every component of strain. That's all this says. It says, I'm going to start with this one. This is going to be the simplest one I'm going to do, and go from there. And so we start there, and then you start working your way down. It never stays at 81. I mean, you think about symmetry of sigma, symmetry of epsilon, and then you think about strain energy. Great qualifying exam question. How many constants you end up with there? I'll let you work through that. And then you basically start working through your, this has to do with symmetry of our quantities. And then you start looking at the symmetry of the material symmetry. And in the world of metals, we get really lucky because our materials are pretty symmetric. And so we often end up with we have a lot of cubics, and we do some hexagonal close pack, but the machinery of first of all, the machinery of crystallography obviously works for something with a lot less symmetry, and the machinery of anisotropic elasticity also works the same way. The hard part sometimes is getting those elastic constants. So I'm saying that with the strain and this set of elastic constants, I can compute the stress. What about if I wanted to use my experiment to determine the elastic moduli? How would I go about that? Well, again, I always kind of take myself back to the isotropic case. And I think of a tension sample. Load it up. I'm looking for E, so I just have stress, strain. I do a linear regression, and I get So what you need is, though, you've got to be able to measure both, right? I've got to be able to measure the strain. I've also got to be able to measure the stress. So if I think about that, the problem of determining the single crystal moduli, we have the same issue. We need something. We need something for both of those. So, and you need enough independent measurements, because maybe you have, depending upon your crystal class, you have multiple components of it's not E and nu anymore. So these are just things to think about, in that how would you go about measuring those in a diffraction experiment? Not trivial. And what about, can you do it with a polycrystal? And what do you need to know? Well, the answer is that you actually kind of need to simulate for a polycrystal, you have to simulate the experiment. Because here's one of the things, and I didn't emphasize this probably strongly enough, but one of the things that comes out of all this stress business let's redraw the thing I just drew. Lots of crystals in here. Sigma macro. The crystal. So here's a question. I want you to all answer this. So I'll hold you to you have to be honest with yourself. I may not be able to write down what this number would be. So this is some number. This is just the load over the area. This is P. And the area is the cross-sectional area. On the micro scale, on the crystal scale, I may not be able to write down the actual number, but do I know where the zeros go on the micro scale? So here's what I'm asking. I'm going to bias your answer. I have these anisotropic units in here. So I have these little guys that are like this. Maybe that's sort of, I'm going to put these little FCC. One's oriented like that. One's oriented like that. I've got all these guys at different orientations. And I have this stress being applied in the far field, being applied way far away from these guys. Can I just look at this matrix and tell what these stress matrices look like? And I'm wanting to see lots of heads going like this out there in TV land. This is a pretty complicated boundary value problem. And one of the things that came, the first things that come out of these experiments is that sigma. So you are at the crystal scale. You are not in P over A-ville anymore. For a polycrystal, it is not it's some multiplier times P over A. It's not this. It'd be really unusual if it were. We get full stress tensors at the crystal scale. Now, certainly, if it's loaded in tension, it will bias this. But what that means, but it's a fully multi-axial stress state. And for those of us interested in plasticity or fracture or anything else, knowing that the stress is not just uniaxial anymore kind of changes your life. So here's another important point that I'm almost finished, and I'd be remiss if I didn't say this. There are ways to take There are ways to take orientation data measured using other modalities, such as EBSD, calculating the orientation matrix, and then you will actually can click on a button in the software for EBSD. It will calculate for every crystal. It will calculate the Schmidt factor. Now, Schmidt factor assumes this. Okay. So, I just said it's not this. So, what I want you to do, if you guys are EBSD people, I want you to go and I want you to disable that button so that you never ever calculate a Schmidt factor looking just at the orientations. You've got to have more than just the orientations. But this is one of the biggest points that comes out of this is that this is a rich and complicated stress situation on the crystal scale, and that's kind of what opens up the doors to the things that you guys are working on. Is that there's a difference. There are going to be some crystals that are good, some crystals that are bad, some crystals that are in a bad neighborhood, you know, but they're not necessarily going to be loaded in the uniaxial tension. So jerk that button off of your EBSD system, and we'll see you next week.